many protons, neutrons, and electrons are in the selenide ion? What do we think? So we want to figure out protons, which we know is Z, electrons, and then the neutrons. So how many protons do we have in selenide? 34, right? Because that's the atomic number for selenium. How many electrons do we have here? 36, good, right? Because we have a 2- charge, right? So that means it gained an additional 2 electrons. And then how many neutrons do we have here? Should be 45, right? And how do you get 45 neutrons? Right, is there anything on the periodic table that tells you how many neutrons you have? So, good, so you can figure out from what you have on the periodic table, right? Because you know mass number is equal to protons plus the neutrons, right? So on the periodic table for selenium, you have the mass number, you have the protons, you can subtract to find the neutrons, right? So the mass number is 79 minus 34 protons gets you 45 neutrons. So what's our answer choice going to be here? B, good. Okay, and this one, this exact question, she told me this will be on the exam. So it's going to be towards like the end. So just make sure you know this, okay? Any questions on number 1 here? Okay. All right. Good with that before I erase it. I can't scroll without it, so. Okay. Number 2 here, and this is the type of question that she does like to ask on the in-person questions. She likes to ask a lot of these like multiple select problems. So number 2 says, identify the parts that best identify with a combustion reaction. So 1, we have a hydrocarbon, water, carbon monoxide, and oxygen. 2, we have a functional group, carbon, water, oxygen. 3, we have a hydrocarbon, oxygen, water, carbon dioxide. 4, hydrocarbon, oxygen, base, water. 5, we have carbon, water, oxygen, carbon monoxide. Or 6, an organic compound with carbon and hydrogen, oxygen, carbon dioxide, and water. So which of these statements best match with a combustion reaction? What you said, B? D. D, good. So statements 3 and statement 6, right? Remember, a combustion reaction, you have a your reactants, right? You have a hydrocarbon, so it's a compound that's got hydrogen and carbon, right? Hence the name hydrocarbon. So say something simple like methane. What's the other reactant of combustion? Oxygen. Oxygen. How do we write oxygen? O2. O2, good, because it's a diatomic element. And what are the products of combustion reactions? H2. Good. Water and carbon dioxide. Okay. So let's look at like what's incorrect here, right? For 1, this is incorrect, right? Carbon monoxide. 2, functional group, that's incorrect. 4, a base, that's garbage. And 5, carbon monoxide also. That's not good, right? So 3 and 6 are correct here. Okay, any questions with combustion for number 2? Okay, here, number 3. So you have an 11.5 gram coin, and it's thrown into a 950 milliliter tank, where it raises the volume to 956.7 milliliters. what is the density of this coin? So I'll give you guys, if you haven't done it already, I'll give you a little bit to think about it, work through it, and then we'll go over it momentarily. Okay, so what are we solving for? We're solving for the density, right? So what is the equation to solve for density? Good. Density is the mass divided by volume, right? So mass, do I have that?
Yeah.
Yes, right? I give it to you here. And do we have the volume of this coin here? No. So what can we do to get that?
The 956.7
Good. So remember, if the volume is not given to you, there's two ways you can get volume. If you have a solid, you can do the volume is length times width times height, right? Another way you can get volume is by the displacement of something, right? So here you're taking a coin, right? You're putting it in water. Initially it's at 950, then it raises the volume to this final volume, right? So to get the volume, you can just solve for the displacement of this, right? So what is the volume of the coin? 6.7, right? And I swear I didn't do this on purpose. I wrote this problem way before 6.7 was a thing. All right. So we have the mass, we figured out the volume, and we plug into our equation. Density is the mass, which is 11.5 grams, divided by the volume, 6.7. And what's my density here?
7.6.
1.71, and what are the units? What are the units of density? Good. Gram per ml.
Liters.
No liters there. For your homework it does, but for this exam, no, it's multiple choice. So, I mean, we're good anyways because we would use 3 sig figs, right? So we got 3 here, and this has 3, so that's fine. Okay. Any questions with number 3 on density there? Okay. Next page, number 4. This says a particular liquid boils at 31 Kelvin. What is the boiling point expressed as a unit of Celsius? Say D. Good, it should be D. And how do you get negative 242 Celsius?
270.
Good. So when we're doing temperature conversions between Celsius and Kelvin, right? That magic number you got to know is 273, right? Or 273.15. So going from Kelvin to Celsius, you subtract 273, right? So 31 minus 273, and that gets you negative 242 degrees Celsius. Okay. Good enough. Hopefully that's not too bad. Okay. Okay, number 5 here. You guys want, you can shut that door. Just, I don't want people getting lost with that, the thing being locked. Thank you. All right, number 5 here. So this is going to be a dimensional analysis problem. The fastest exit velocity ever recorded on a batted ball in Major League Baseball was hit by O'Neill Cruz in 2025 with a home run measured with a velocity of 122.9 miles per hour. Convert the velocity into feet per second. And here I provide you the appropriate conversion factor that 1 mile has 5,280 feet. So, right, what are we starting with? We're starting with miles per hour. So what does miles per hour look like set up as a fraction? Good, it's miles over hour. And what do I want to convert that to? I want feet per second. Right, so my miles get converted to feet, which this conversion factor is given to you here, right? You're not expected to know that. And then hours converted into seconds. Okay. So if you haven't done that, I'll give you a few to work on that, and then we will discuss that. All right, so just sorry to interrupt, but a new thing I have to do. Any people that come in late or in between when the QR code is up, you just have to sign in manually. So you're going to enter your full name and then your Z number. So if you scanned that code earlier, you're good. You don't have to sign this. But if you did not scan that code, just write your name. I'm gonna just pass it around here. All right, thanks. How are we doing so far on this? Anybody have an answer? What do we think?
180.3.
Yeah, about that. So just depending whether you round, I guess I didn't. I have 180.25, but not a problem, right? So again, we're going from miles to feet and hours to seconds, right? So I think it's best practice to start converting with your whatever unit is on the numerator here, right? So I want to convert from miles into feet. So for this unit of miles to cancel away, where does it have to go on this next fraction here? On the denominator, right? Miles on the bottom. I'm solving for feet, so that's going to be on the top. And from this info that I give you here, you know that 1 mile is 5280 feet, right? So from here, your unit of miles cancels off. And now we have feet per hour, right? But we want feet per second. So now you've got to deal with this unit of hours, right? So for this unit of hours to cancel off, where should this go now? Got to go on the top, right? It's always going to go opposite of where it's at. And what unit should be on the bottom here?
Seconds.
Seconds. And so what's bigger, an hour or a second? An hour, right? So how many seconds are in 1 hour? 3,600, right? In 1 hour, there's 60 minutes. 1 minute has 60 seconds, 60 times 60, 3,600, right? Now your unit of hours canceled away, and what are you left with? You have your feet over seconds, right? So just as a reminder of how to calculate the dimensional analysis, any number that's on the numerator you will multiply, any number on the denominator you'll divide, right? So 122.9 times 5280 divided by 3,600, you're gonna get 180.25 feet per second. Okay. Everybody good with that? Any questions? Good. Can I erase here? Okay, number 6. Which of the following measurements are incorrectly paired with its SI unit? And there are multiple correct answers here. I heard someone say D, right? So D is an answer. And C as well. Right? So the SI unit of temperature is Kelvin, so that's good. The amount of a substance to the mole, right? We've gone over the mole extensively the past 2 weeks, so that's good. What's the SI unit of mass? The kilogram. Good. What's the SI unit for length? Meter. And the SI unit of time is second, so that is good. So C and D here are your answers. Okay, any questions about that? Thank you. Any questions with number 6 there? Does that make sense? Okay. All right. I'll give you a moment to look at number 7 and fill this one out. And you can get your answer here from looking at the periodic table. All right, so which of these atoms would you expect to make a -3 anion? Good, it's going to be B, phosphorus. And why is it phosphorus? Good, because it's in group, it's in group 15, and it makes a -3 charge, right? Okay, any questions with that? That's just from knowing the common ion charges, right? Okay, any questions on page 2 before I move on? Okay. Number 8, the element antimony has 2 naturally occurring isotopes. And here in this table, I provide you the natural percent abundances as well as the isotopic masses for the 2 isotopes of antimony. So your job here is to calculate the atomic mass of naturally occurring antimony. Right, so who can remind me what the formula is to calculate average atomic mass? Yeah, perfect. So remember the formula we learned in chapter 2 is the percent abundance divided by 100 times the isotopic mass plus percent abundance over 100 times isotopic mass. And right, you do that for each isotope that you have, right? So if you've got 5 isotopes, you got to do that little, percent abundance times mass 5 times. Here, you only have 2 isotopes, so we've only got to do it twice, right? So, let me write it up here. So, what's my first percent abundance? 57.21 over 100, right? So in other words, you're just changing this percentage into a decimal, right? And what's the mass of my first isotope? 120.904. Okay, so that's for isotope 1 here. And now we've got to do the same thing for the second isotope. So my other percent is the 42.79 over 100 times the mass, which is 122, and this is going to get messy, 0.904. And so what do you get for the average atomic mass? Yeah, you should get B, right? When you calculate this, you're going to get 121.759. And by the way, what are the units for average atomic, for atomic mass here? Good, AMU, or you can just use U, means the same thing. And so B is our answer because this 7.5 is just rounded, 7.6. Okay. So don't freak out if your answer doesn't exactly right match here. There, it could be a rounding thing. Okay. Any questions on number 8 or on how we solve that, or about the formula?
Dividing each percent abundance by 100. Multiply the mass one by the percent abundance ones, and then same thing for the second, and then divide the whole rate by 100.
I don't know if I've never tried it that way. It might work, but I would do it this way. Or if you want, you could just change this right away to a decimal, because that's what this is doing. But doing this times this plus this times this divided by 100 at the end, it might work, but also your calculator, it might like flip around that like order of operation, so it might give you like a funky number. Okay. Everybody good with number 8 here? Can I erase this? Okay, so number 9, we're going over some nomenclature here. So I've got a few examples where we have to write the name from the chemical formula or write the formula from the name. So MgCl2, what's this? Good, magnesium chloride. So remember, when you're naming compounds, right, you need to figure out whether the compound is what? What's the distinction you have to make?
Ionic or covalent.
It's ionic or covalent, right? So remember, ionic is a metal and a nonmetal. Covalent is nonmetals, right? So magnesium we know is a metal, and the chloride here is a nonmetal. So remember, the anion, right? The second element, the suffix gets dropped and it gets replaced with ide, with IDE. So MgCl2 is becomes magnesium chloride. What about, so here for number 2, I'm giving you the name. What's vanadium 5 sulfide? What's the formula for that?
B2S5.
Good, it's going to be B2S5. Okay, as a reminder, remember how to determine those subscripts, right? Remember we have to do what I called the drop and swap, right? You've got vanadium. What's the ion charge of vanadium here? +5, right? That's what this Roman numeral means. Sulfide, what kind of an ion charge does that make? -2, right? Because it's in group 16. You drop and swap, right? So the 2 goes to the vanadium. That 5 goes to the sulfur, to the sulfide, right? Now remember, the whole reason of doing that is because when we make ionic compounds, we have to make them so that they are electrically neutral, which means a net zero charge, right? So if I take my V2S5 and I break it apart or ionize it, right? You get 2 vanadiums, right? What was the original charge of vanadium? +5. And if you break apart the sulfur, how many sulfurs are you gonna have? Well, hold on, let's do it this way. So this is here for vanadium, right? So what's 2 times +5? +10, right? Then you take the sulfur and you break that up, right? You've got 5 sulfurs, and sulfur has a -2 charge. 5 times -2 is -10, right? And do we agree that +10 and -10 equals 0? Yeah, right. So this equals 0, and that's why you have a net 0 charge. So that's why the drop and swap works. Okay, so here's our formula for vanadium 5 sulfide. Okay, any questions on that one? Good. Cool. Okay, next one. CCl4. Good. So this is going to be carbon tetrachloride. So what's the deal with this tetra here? Good. So there's 4 chlorides, right? But where does that rule come from? CCl4, is this covalent or ionic? Covalent, right? So when you have covalent compounds, remember you have to use those numerical prefixes to indicate how many of that atom you have, right? Now, why doesn't this say, so we have, right, 1 carbon, 4 chlorines, right? That's where tetra comes from, it's 4. Why isn't it monocarbon for 1 tetrachloride? Yeah, right. It's an exception to the rule, right? When your first element has if it's supposed to have a prefix of 1, you omit that prefix, so you just ignore it, right? Yeah.
It was C2, see that one
Yeah. Okay. Does that make sense? Do we remember those rules from a little bit ago? Okay. BF3, what's this going to be? Good. Boron trifluoride. So this is also covalent. And also, I keep saying covalent compounds, right? What's another synonymous term for covalent? All right, so you're a little ahead. We're learning that later on, but there's another name for covalent. Yep. Yeah, good. Molecular, covalent or molecular. They mean the same thing. Okay, so just make sure you know that. And so later on in the course, we're going to go pretty deep into covalent compounds and those structures that they make. When we get to chapter 8 later on. All right. Good with BF3 here? And then finally here, H2PO4, what would we call that? Good, this is dihydrogen. Hydrogen phosphate. Right, PO4, we know this is the phosphate ion, right? One of those polyatomic ions that I know we all have memorized by now, hopefully. Pretty please. And then you have two H's, right? So it's dihydrogen phosphate. Hey, any questions with naming or any of the rules that go for naming? You have a question in the back? No? Yeah,
Yeah, number 7 again.
number 7.
Okay, I
It would
got
be B, phosphorus.
Thank you.
Yeah. All right, are we all good to move on from naming here? All right, awesome. All right, number 10 here. Newly synthesized compound X is run through both mass spectrometry and elemental analysis. Compound X has a molar mass of 266.65 grams per mole, and it has the following composition. So, mass spectrometry is it's an experimental analysis to find out the mass of a compound, right? So that's how we get this through mass spectrometry. And then the elemental analysis, kind of like what it sounds like, right? It's going to tell us what elements are in there. So what this tells us here is aluminum, we have 20.24% aluminum, and we have 79.76% chlorine. From the given information, we need to figure out what is the molecular formula for compound X. Okay, so I'll give you a little bit to let that simmer, think about it, and then we'll go through the steps to solving this. So what are we thinking? What so first, like, what top question or an answer? So give me 1 second. What topic of this would we have to do to be able to figure this out here? What do you think?
So you would take the mass percentage and just, instead of, you would move the percentage and just put grams on it.
Okay, so yeah, I like the idea of that. So what's that like leading up to? What do you
So essentially you can get up some numbers of each specific element. So then you would basically set it up so it would be 3.24 grams of aluminum times 1 mole of aluminum over, let's say 20 grams of aluminum.
Yeah.
You would do the same thing with fluorine and then you basically divide by its atomic mass.
Good. So essentially what we're doing here is I think I heard in the back, you've got to figure out empirical formula. Empirical. Right? Figure out the empirical formula. From there, you can figure out the molecular formula. Okay, so just like we set up here, first you need to figure out the empirical formula, right? So when you get this, right, what's the first thing you can assume about this sample? How much do you have? So that's the molar mass, but I'm asking about the sample of compound X. So when we're determining empirical formulas, what's the first thing you assume? Good, so you assume you have a 100-gram sample, right? That way, these mass percentages, right? Instead of writing it as percent, you just write it as grams, right? Because if you add these up, it equals to 100. So in other words, here we have, I'm gonna scroll down here. So in other words, we have 20.24 grams of aluminum, and we have 79.76 grams of chlorine. Right, so you convert your percentages into grams. From there, just like she said, we're converting from grams to moles, right? So what do we have to use to convert from grams to moles? The molar mass, right? So converting grams to moles, right? The gram is on the bottom, the mole is on top. You're dividing by the molar mass, right? So of course you find molar mass from the periodic table. The molar mass for aluminum is 27. And the molar mass for chlorine is 35.45 grams in 1 mole. Okay, so how many moles of aluminum do you get with this mass? Good, so I have 0.749. And what about for the chlorine? 2.249 and moles, right? Okay, everybody good so far? Okay, so we converted everything into moles now, and what's our next step from here? Good, so you're gonna divide by the smallest number, by the smallest amount of moles. So hopefully we all agree that 0.749 is smaller than this 2.2, right? So we're gonna divide everything by 0.749. Okay. Once you divide here by the smallest amount of moles, what is that giving you? It's going to give you the simplest ratio of the atoms, right? And I'm going to explain what I mean there by ratio in a minute once we finish this problem. So for aluminum here, right, 0.749 divided by itself is what? Just 1, right? So this 1 goes with aluminum. And for the chlorine, what's 2.24 divided by 0.74? It's going to be 3, right? So 3 goes with the chlorine. Okay, is everybody good so far? Anybody lost? Okay. So, like we said, this is giving you the ratio, right? Once you divide here, this is giving you the simplest ratio. In other words, it's giving you the empirical formula. So what's my empirical formula? Good, it's AlCl3. Okay. So can we answer our question from here? No, right? Because I'm asking for the molecular formula. So don't get fooled and think A, right? No. We found the empirical formula, now we got to do an extra step to get to the molecular formula. Okay? So is everybody good with this math here so I can erase and write? So I'm going to leave this up here because we need that. Okay, so first step, we need to figure out the empirical formula. Now we can move on and find the molecular. So, to figure out the molecular, right? How do you? Does anyone remember how you can get the molecular formula? Good. So you're going to take the molar mass, right, which is given to you here, divided by the molar mass of your empirical formula. Okay, so that's why we had to first figure out the empirical formula in order to do this division here. Okay. So when you divide these numbers, right, whatever your quotient is, you're going to multiply that number to every term, to every subscript here in the empirical formula, and then that will give you the molecular formula. So what's my molar mass here? Good, the 266.65. And what's the molar mass of the empirical formula that we just figured out? I hear two numbers. What I have is 133.35. Right, so you would do for the empirical formula, right? You look at the periodic table, 27 plus 35.45 times 3. And what number do you get when you divide molar mass by the empirical mass? Good, you get it's like 1.99, I think, something like that, right? So 1.99, that's 2, right? You can round that up. So now with this number 2, right, our quotient here, you're going to multiply that to every subscript in our empirical formula. So the subscript of aluminum is 1, right? 1 times 2 is 2, so you get Al2, Cl3. Sorry, Cl 3 times 2 is 6. Cl6, and you get D as your answer. All right, what do we think about that? Any questions on that? Does that make some sense? Hopefully. Everyone good with empirical and molecular? For sure? We're good? Okay. Awesome. So you'll definitely see this on the exam. It'll be given to you like in a chart like this. This is from the midterm last semester. I just changed out like the only thing I changed was like this part. But yeah. Okay. All right, number 11. Calculate the mass of 8.04 times 10 to the negative 3 moles of oxygen. So what kind of a conversion does this sound like to you? Good, moles to grams, right? I'm giving you the moles of oxygen. I want the mass or the grams of oxygen. So of course you have to first write down what it is you're given, right? So we've got 8.04, 8.04 moles O2. And so what units will have to go on this fraction here? So say that again, we have grams. Good. So moles on the bottom so we can cancel. Grams on top, right? So what's the molar mass of oxygen here? Good, 32. Right? Don't get tripped up and put 16 here, because that's a mistake I see my students make all the time, right? On the periodic table, oxygen is 16, right? But it's O2, so we've got two of them, so it's 32. Your moles cancel off, you have grams left by itself. And so what's the mass of oxygen that we have here? You said? Yeah, good. You should get 0.257 grams of O2. Okay, any questions on number 11 there? Good. All right, any questions before I go to the next page? Am I good to erase here? That is yes. All right, so number 12, read this one carefully. This says, calculate the mass of glucose. And if you've taken biology, you know glucose is the sugar that plants make in photosynthesis. So it's C6H12O6. Calculate the mass of glucose in a sample that contains 1 billion, which is 1 times 10 to the 9, oxygen atoms. Okay, so I'll give you guys a little bit to work through this. If you haven't gotten this, I'd say work with the people around you to try and figure this out, and then we'll go over it in a few minutes, a minute or two.
I'm missing one thing.
Sorry to interrupt while you guys are working, but did anybody who did not scan the QR code not sign this yet? This needs to go around again.
So funny, bro. What? Let me see it.
She's out to get you. What'd you say the other day? She's like, why did you give me that sassy?
Yo, recently, I was like, what? She was like,
All right, anybody have an answer to this problem?
it's like not.
What do we think here?
3 times 10 to the next.
Do we need more time to figure? Do you have a answer to question? Yeah.
It's like, change it from first.
So you got to go atoms to molecules first, and then you can proceed from there. So you can't go straight from atoms to moles. You got to go atoms to molecules first. So just I'll give you guys a little bone here to start. You're going from, right? I'm giving you the amount of oxygen atoms, right? I'm only giving you this in atoms, right? So we're going from atoms to molecules to moles and then to grams. Okay, so there's your little roadmap to start this, and we'll go over it in a moment.
And breathe. That's not really. Yes. No, I'm talking about what I just typed in the group chat.
Yeah.
And I said, I didn't just be, oh, don't please do that. I don't like that. It's not gonna tell you bad. Oh, what?
Keep thinking.
Don't you want that though? What do you mean? What do you mean? I do have one. How do you go? No, I'm looking up how to go out of this.
Do you use Avogadro's number for this?
What was that?
Do you use Avogadro's number in this problem?
Do you use it first to go to molecules or do you use it to go to moles? You use it to go to moles, right?
Yeah.
Yeah, you divide by it, so. So how do
So
you-
the Avogadro's number is gonna be like your second step, not your first. Shit.
This is what, it's just, it's molecules, everything else we do all in one.
We started now. I don't,
Yeah.
we don't remember.
Anybody have an answer here? Anyone get this one? Alright, so let's go over it then. So again, here's the roadmap we're gonna take to solve this problem. We're gonna go from the given amount of oxygen atoms into the molecules of glucose, then to the moles of glucose, and then finally to the grams of glucose. Okay? So what are we starting with here? Yeah, right? We have 1 billion, which is 1 times 10 to the 9 oxygen atoms. Right, that's the information you're given, that's the only thing you can start with here. So what did I say the roadmap was? I said we were going atoms to molecules to moles to grams. Okay. So let's do this jump here from the atoms, which we wrote down, into the molecules. So atoms I want to cancel off. And I want to solve for the molecules, right? So what type of atom are we canceling away? The oxygen, right? So in this molecule of glucose here, how many atoms of oxygen do we have? 6, right? So 1 molecule of glucose has 6 atoms. Okay, so at this point now, I'm in the molecules of glucose, right? Okay. So we're here now, right, at the molecules. Now we have to go to moles. So how can we convert? Is there a set way that I can go from the molecules or the particles into moles? You got to use Avogadro's number, right? And who can remind me what that is? Good. So remember Avogadro's number. And like I said when we first learned that, you're gonna memorize this number like it's your phone number. Right, so my oxygen atoms cancel, my molecules cancel. Now I'm in the moles of glucose, right? So what's our final step gonna be here? Go to the grams. So how do we go from the moles to the grams? Molar mass, right? So what's the molar mass for glucose? Good, it's about 180, right? I might have rounded different. I have 180.16, which, whatever. Right, so let's recap our units going again, right? And with stoichiometry, it's really important that you're writing out all of your units in every step so that you can see that they cross off, right? Give me 1 second. If your units are not crossing off, the way they should be, you're doing something wrong, right? So let's double check ourselves. The oxygen atoms go away, right? We went from the oxygen atoms to the molecules of glucose. Now the molecules of glucose go away, right? We converted that into moles. From here, the moles of glucose go away, and you just have the grams left. So, who has an answer? And Maya, did you have a question?
There was one. There was, they already gave it to me. Maybe it was. That I got wrong. So that. It is. Oh my God, this is always more.
Avogadro's number, it could be molecules, atoms, ions. But so anytime you're going from so the vague term is like particles, right? So molecules, atoms, ions. Anytime you're going from particles, so here in this case, molecules going to moles, right? So if you were in the molecules, we want to go to the moles, you can only do that by Avogadro's number. And it's got to go on the bottom of the fraction here, right? Because this unit needs to go away. So, it's got to be opposite, right? It's got to go on the bottom. So that's why the Avogadro's number is on the denominator. Does that make sense? So what's our answer for 12? What's the mass of glucose? A really small number. Yeah, good. So you should get, I'll do it in blue here. 4.98 times 10 to the negative 14 grams. Any questions on that? Yeah.
Then I did. What little papers we talk. It's just like. And then I did the last one. So it's like swap this here and did.
Yeah, that should be fine. As long as your units are like going away, then that's fine. Atoms to moles.
Yes, I did. I just didn't. Like, so the short one is so.
So you swapped up. Yeah, that's fine because you're. Yeah, that's fine. Yeah. If it works, yeah, that's fine.
Well, we was
You would need 1 sig fig. So you would say this is 5 times 10 to the negative 14. Okay, are we good with number 12 there? Okay. Can I erase this? And even if you don't get it, I'll publish the answer key tomorrow. Okay, number 13. What is the percent composition of manganese in potassium permanganate? So we've got to know 2 things here. We have to know the chemical formula for potassium permanganate, and we have to know the equation for percent composition. So what is the formula for potassium permanganate? Yeah, KMnO4, right? K. So permanganate is MnO4 minus, right? That's a polyatomic ion you need to know. And then you add the potassium in there, right? You do your little drop and swap thing. So your formula is K MnO4. Okay, cool. So we know the formula, right? And what's the equation? What's the formula to solve for percent composition? Remembers that. Yeah, what do you think? Close, you're missing just one thing. Okay, so I guess that's another thing, but there's one more thing that goes on the numerator here. So when you're doing percent composition, right, you're going to be solving for a specific element, right? So it's the number of atoms of that element times the molar mass of that element divided by the compound's entire formula weight. And I already gave that to you here with the molar mass, right? Molar mass, formula weight, it's the same thing. And then also, sorry, I always forget this, you times 100 to make it a percent. Okay. So we're solving for manganese, right? And then, so did anybody solve this? How did you, or would you get at least? What answer choice is correct here?
I think that's formula.
Yeah.
Mhm.
Was that?
So I get multiplied.
Yeah, it's the same thing. Yeah. Yeah. It's the molar mass of this thing. So I already gave it to you here to save some time.
Okay.
So like, I know it's kind of formula weight, molar mass, molecular weight, molecular mass, atomic, it's all the same thing. So anybody have an answer for this? What's the answer choice? Yeah, it should be A. Right, so how do you get there? So we're solving for manganese, right? So we're following with this formula, right? So how many atoms of manganese do we have? How many manganese do we have here?
One.
Just one, right? What's the mass of manganese in the periodic table? Yeah, it's about 55, right? And what's my formula weight? If I didn't give this to you, how would you figure that out? It's the molar mass of this whole thing. So you add K, Mn, and then the 4 oxygens. But here, right, potassium permanganate, I gave you the molar mass to save some time. So it's 159. So essentially what you're going to do is 55, right, 1 times 55, which is 55, divided by 159 times 100. From there, you're going to get 34.59%, and that's A, right? It's just rounded a little bit. Okay, any questions with percent composition there? Good on that? Any questions? Okay. All right, number 14 list the 7 strong acids and the 5 strong bases. I'll give you guys some time to jot it down and then we'll go over it. All right, so here we're listing the strong acids and strong bases, right? Remember that you are responsible for memorizing the 7 strong acids and the 5 strong bases, right? So what makes an acid or a base strong? So, okay, I'm here. So I'm saying, what did you say again, Peter? Okay, so it dissolves in water. How does it dissolve? Or let's use a better chemical word, dissociate, right? Put on your science caps. How is it going to dissociate in water?
It's strong and completely.
It's gonna fully dissociate to its ions, right? That's what discerns something as strong versus weak, right? So we know that strong acids, strong bases will fully ionize, fully dissociate in solution, whereas weak acids and weak bases, they will ionize, but only partially, right? So, who can list me some strong acids? HCl, right? So hydrochloric acid, that's in our stomachs, right? That's stomach acid. HBr, good. HI. So let's list them out, and then I'm gonna remind you guys of that acronym that I taught you back when we did this a few weeks ago. So we have sulfuric acid, hydroiodic acid, that's supposed to be an I. Hydroiodic acid, hydrobromic acid. We have nitric acid, hydrochloric acid. What is that? 4, 5. Then we have perchloric acid, and then chloric acid. Okay, so these are the 7 strong acids. You need to know the name of it as well as the formula for it. Okay. So if you remember the acronym I taught you guys, it works for 6 of them, and that extra one you just have to memorize. So remember, so I brought no clean clothes. Okay, and that this acronym, it kind of goes in the order. It goes in the order of these acids that I listed out, right? So, for right, sulfuric, I, hydroiodic, brought, the Br, hydrobromic, no, nitric. The Cl for clean is hydrochloric, and then ClO, the fluids, is perchloric. And then this extra one is chloric. So just make sure you know the difference between per chloric and then chloric. Okay. Any questions on the 7 strong acids? Okay. Can I get rid of this? So those are the acids, right? And the acids are pretty easy to identify because they typically have that H in front, right? And so we know acids, right? What do they do with that H? They donate protons, right? They'll donate a hydrogen. So there are these strong acids. Now let's look at the strong bases, and there's 5 of them. So what polyatomic ion do a lot of the bases have? Hydroxide, right? So what are the 5 strong bases we have? We've got good. Good. So we have sodium hydroxide, lithium hydroxide, potassium hydroxide, barium hydroxide, and strontium hydroxide. Okay, so those are the 5 strong bases that you need to know. Okay, and a lot of them are right, notice it's a lot of these are the alkali metals and these are the alkaline earth metals. And any questions about the strong bases here? Yeah. So these are made of the alkali, right? Because notice there's no subscript there, right? Because the alkali metals make a +1 charge, and hydroxide we know is -1. The alkaline earth those make a +2 cation, right? So that's why the OH has that subscript of 2. Because that 2, right, the drop and swap, it comes from up here. Good. Any questions on number 14? Strong acids, strong bases? Yeah, so good question. She asked, what about calcium hydroxide? Calcium hydroxide is a strong base, but for the purposes of this class, we say it's not. So I know it's confusing. There's also, I think, like 2 more strong bases, but just know these 5 for this class, okay? And like the reason that we say, it's kind of confusing, I don't really agree with it, but the reason that the professor says calcium hydroxide is not strong is because it doesn't dissociate that well, which I don't know. I don't make the rules, so. All right, so just know these. All right, any questions on that? All right. Next page here. Number 15 says balance the chemical equation below using the smallest possible whole number stoichiometric coefficients. And then the question I'm asking you is, what is the sum of stoichiometric coefficients in the balanced equation? Good, so I'm gonna bring that up. In this case, so remember, we were bouncing. Remember, like that little quick tip was like to count your polyatomics as a unit. In this case, you cannot because, right, what polyatomic do we have here? Phosphate, right? But we don't have another phosphate on the other side. So you can't count it as a unit. In that case, you have to separate them. Yeah, so when it's on both sides, you can count it together as a unit, but when it's not, right, you don't have another phosphate to compare to, so we've got to break it up into the P and the O. Yeah, like if I had, say I had a PO4 here, then you would keep together. But we can't do that here, unfortunately. Okay. What are we thinking so far? Anybody have an answer? Yeah, what do you think?
The first one.
Well, so what's what answer here? C. Okay. Anybody else have C here?
B.
You got A. Anybody else?
There's a one, yeah.
Yeah, I don't know, but I've got a different answer here. What do we think? No.
I think we should just do the prompt.
Right, so let's, the answer here is B. Okay. So let's see how we get to that. How many calciums do we have? How many P's do we have? 2. How many O's? 10. Right, we have 8 here, 4 times 2 plus 2 more, 10. We have 1 silicon and we have one carbon. Right? On the product side, we have 1 calcium, 4 phosphorus, 5 oxygen, 1 silicon, and 1 carbon. Right? Now, someone brought up, why don't you count the polyatomic, the phosphorus, as 1 unit? Right? Remember we were doing that, we were balancing equations. That little shortcut does not work here because you can only do that when you have the same polyatomic on both sides. So we don't have phosphate here on the product side, so you can't keep it together, right? You've got to separate the P and the O's. Yeah. Why do I do the? What do you mean by that?
Why are you balancing the oxygen as the third thing when it shows up in?
I mean, this doesn't mean the order I'm balancing it, it's just the way that I wrote it out. The way that I like to write this is, I write these in the order that I see them. So calcium, phosphorus, oxygen. But that doesn't mean I have to balance calcium first. You can do whatever you want. Okay, so let's see what we could balance with first. Let's look at the phosphorus first, right? So phosphorus on my product side I have 4, whereas on my reactant side I have 2. So how can I get 4 on this side? Put a 2, right? So that way that's going to give me 6 calciums, 4 phosphoruses, and how many oxygens? $18, good. Right, so that's what changes here by putting this coefficient of 2 in front of the calcium phosphate. Now let's look for, these are good. Let's look at calcium now, right? I've got 6 here versus 1. So let's use a 6. Right? That gives me 6 calciums, 6 silicons. And how many oxygens do I have now? I've got
18.
So we've got 6 times 3, which is 18 plus 2, so 20, right? Okay, so we've got to keep on going, right? Let's look now for silicon here, right? How many do I need? I need 6, right? So let's put a 6 here. So that gives me 6 silicons. How many oxygens do I have now? 28, right? Good. So let's see where we're at. Calcium is good, phosphorus is good, oxygen not yet, but the silicon is good, the carbon is good. So we've got to deal with the oxygen now, right? So what do we think we should do there? A 5 where?
Just run back to the
If I put a 5 here, five plus, yeah, I get, right, so 10 plus 18, 20. And then how many carbons do we have? 5. Oh, maybe I did this wrong, actually. Damn. Yeah, this is good. It's about, yeah, so I totally did this wrong. So just make sure you write on the answer, because I already some answer came. So what's my sum? I've got 2 plus 6 plus 5 plus 6 plus 1 plus 5. 6 plus 6 is 12 plus 5, 17 plus 2 is 19 plus 6, 25. So good job, guys. I messed up on this. All right. So ignore the answer key because this is going to be incorrect on there. Okay. All right. Any questions on number 15 here? I know this one was kind of long-winded, but. Can I erase here? Okay. Okay, number 16 here. Dinitrogen monoxide, commonly known as nitrous oxide or laughing gas, has many medical uses for its analgesic effects. Analgesic, does anyone know what this means? It's pain reducing, right? So nitrous oxide is industrially produced by thermally decomposing ammonium nitrate into dinitrogen monoxide and water vapor. And we're going to consider the following questions. So dinitrogen monoxide, laughing gas, right? Has anybody here had their like wisdom teeth pulled out or any type of like oral surgery, right? So you might have been given this, right? They give you like that funny little mask on your nose, right? And it gives you this gas, the dinitrogen monoxide, right? And right, it's pain reducing, and you probably got like super high from it, right? So it's produced by thermally decomposing ammonium nitrate, right? So you take ammonium nitrate and you give it a bunch of heat. So what is ammonium nitrate? What's being decomposed here? Good. NH4, NO3. Gosh, NH. NH4NO3, right? So you take that, you give it a bunch of heat, it decomposes or breaks down into water, which we don't care about, and the N2O, which is laughing gas, right? So suppose you wanted to produce 3 liters of laughing gas. What mass of ammonium nitrate would you need to decompose? So I want 3 liters of this, right? I want to figure out what mass of ammonium nitrate I need to start with to obtain my 3 liters of laughing gas. Okay, and in order to do that, here I give you the appropriate conversion factor that 1 mole of a gas is equal to 22.4 liters. So what do we have to do? We've got to go from the liters of laughing gas to the moles, right? From there, we can go from the moles of laughing gas to the moles of ammonium nitrate, and then to the mass of ammonium nitrate. Right? So what should we start with here? Three liters, right? 3 liters of laughing gas, which is N2O. So is this unit liters any use for me? So like yes and no, right? I can't do any conversions with liters, but I can do conversions with moles, right? So I want to get rid of my liters and I want to go to moles. And I know that 1 mole is 22.4 liters. Okay, so we are in the moles here of N2O, right? What's my next step? Good, the mole ratio, right? So we're in the moles of N2O, but I want to figure out the quantity of the ammonium nitrate. So remember, the only way I can jump here from these different chemical species is through the mole ratio, right? Moles is the only unit that can interrelate these different quantities. So with this 2 I gave you here, the equation's already balanced, right? So you don't have to worry about that. But of course, you would check that first. So I want to get out of the quantity of N2O. I want to get to the reactant there, right? So what's my mole ratio here? 1:1, right? Now that I'm in the moles of ammonium nitrate, what can we do from there? Get the mass of it, right? And we can solve our problem. And what would you use to get to the mass? What would you use there? The molar mass of ammonium nitrate, right? Does anybody have that handy? Yeah, it should be 80, right? So in order to produce my 3 liters of laughing gas, how much ammonium nitrate do we have to start with? Yeah, good. So you should get about, and I'll write this up here if you don't have room. I've got 10.71 grams of ammonium nitrate. Okay, any questions on that? Okay. Am I good to erase? That was part B. Part C says in order to decompose ammonium nitrate, you have to heat it up to a temperature of 250 Celsius. What is this temperature in Kelvin? So what's 250 Celsius in Kelvin? Good. 523, right? So you take your temp in Celsius plus 273, and you're gonna get 523 Kelvin. Okay, and it's a little weird notation here is that Celsius always gets that degree sign. I don't know there's like a word for it, I don't know what you call it. But Kelvin does not, so it's just the number. Okay, everybody good with that? All right. Number 17 here, label which species is oxidized, which is reduced, and then determine the oxidizing and reducing agents. So remember, in order to solve these redox reactions, you need to first assign the oxidation numbers to all of the elements in your compound, right? Then from there, you can, compare both sides and see what's changing, right? So remember, we use the acronym oil rig. Right, so remember, oxidation, what is that? Good, oxidation is the loss of electrons. Reduction is the gain of electrons. Okay. You remember oil rig? Okay, cool. So now let's assign the oxidation numbers here. So what's the oxidation number for copper here in the copper 2 sulfate? Positive 2, right? What's sulfate? Negative 2, right? And we know that this is correct because we have a neutral compound, right? So when you have a neutral compound, the sum of the oxidation numbers has to equal the overall charge, right? So positive 2 plus negative 2 equals 0, right? Moving on to the potassium iodide. So what's K? Plus 1. What's I? Negative 1. Good. Then we move to the product side. So now we have copper iodide. What's copper? Good, so it should be plus 1, right? So these numbers have to equal to 0, right? So remember, copper, it can change its oxidation numbers, but iodine is a halogen. So what are most of the halogens? Negative 1. So in order for this to be 0, the copper has to be plus 1. And then what's the oxidation number of the iodine? Yeah, question?
Separate.
Yeah, so good question. With the polyatomic, a little trick you can use is just assign the charge as the oxidation level. So sulfate, we know is negative 2. So you can just group the whole thing together and make it negative 2. Okay, it's a little shortcut. So now we're on the product side, right? What's the oxidation number of iodine here? It's 0, and why is it 0? It's a free element, right? So when you have free elements, the oxidation number is 0. Cool. And then we have potassium sulfate. So what's the oxidation number of potassium? So be careful. It's +1, but there are 2 of them. And then what's the oxidation number of sulfate? That's -2, right? So you're only looking at the individual oxidation numbers. You're not looking at what it is when it's in the compound multiplied there. Okay. So now we can make our comparisons and determine what's oxidized, what's reduced, right? So let's look at copper here in the copper sulfate, right? What's happening there? Copper goes from +2 to what? Goes from +2 to +1. So is that getting more positive or more negative? More negative, right? So if it's getting more negative, right, you keep in mind that electrons are negatively charged, right? Are we gaining electrons or losing electrons? We're gaining. So what do we call the gain of electrons? Reduction, right? So here, copper sulfate is reduced. And then what does that also make it?
Oxidizing agent.
It's the oxidizing agent. Yeah.
We don't, on December, yeah.
Yeah, exactly. So good question. When you're giving your response, you don't say copper is reduced, it's copper sulfate, it's the whole thing. Okay, so I'll write that out once we're done here. Okay. What element should we look at next? To compare. What should we look at next? So we should look at iodine and not potassium, right? Because look at potassium. Does that change from one side to the other? No, right? It's +1 here, and it's also +1 here. There's just 2 of them. But iodine, it's -1 here and it's 0 here. So we're going to compare iodine. So from -1 to 0, is that more positive or more negative?
We're negative.
More positive, right? Remember, think of the number line from like elementary math, right? 0 is in the middle. You have your positives on the right side, so +1, +2. And you have your negatives, right? -1, -2. So iodine is going from -1 to 0, right? It's getting closer to that positive side of the number line. So if we're getting more positive, are we gaining electrons or losing those electrons? We're losing. So what do we call the loss of electrons? Oh God, what is that? Is oxidation, right? And so if it's oxidized, what does that have to make it? It's the reducing agent. So how you would respond here is you'd say copper sulfate is reduced, and it's the oxidizing agent. And then potassium iodide is oxidized, and then it's the reducing agent. Okay. So just the agent part, it's always going to be opposite of whatever like is happening there, right? So why that is because let's say so let's look at the Ki, for example, right? We said potassium iodide was oxidized, right? So that means it lost electrons, right? When it loses those electrons, right? When it's happening in these reactions, those electrons, they can't just like chill out by themselves in like free space, right? They've got to go somewhere. So because Ki lost its electrons, it was oxidized, it's the reducing agent because it caused for something else to become reduced, right? It caused for the copper sulfate to take its electrons and it forced it to become reduced, right? And same rationale here with the copper sulfate. It was reduced, so it gained electrons, and it's the oxidizing agent because it didn't just pull those electrons out of thin air. It stole them from somebody, right? So here it stole the electrons from Ki, causing it to be oxidized. Okay, any questions about that? Does that make some sense? We good? Okay, can I erase this? Okay, number 18 here. Write the net ionic equation for this reaction. So what are my products? Right, so remember, to write net ionic equations, we write a balanced equation, complete ionic equation, and net ionic equation. That's what these letters are standing for. So I give you the reactants, right? So what are the products going to be? So, okay, CO is cobalt, right? Not copper. So we have cobalt, sulfide, and what else?
Yeah.
Good, sodium nitrate. Okay, what do we do next? You've got to balance, right? So putting a 2 here will balance it. And then from there, what do you have to figure out? Good, so the states of matter, right? So right on the exam, you're going to get your periodic table and your solubility chart. On my Canvas page in the welcome module, I have the periodic table and solubility chart. That is exactly what you'll get stapled to your exam. So what are the states of matter here? Is the cobalt sulfide soluble or insoluble? It's insoluble, so what state of matter is that? Solid, right? What about sodium nitrate? It's soluble, so that's aqueous. Okay, that's an A. A. AQ, right? Okay, good with the balance equation and states of matter. So of course you're gonna get that solubility chart, you just have to read it, right? Nothing too much more than that.
Do you write certain states of matter first in the product?
It doesn't matter, you can write it whichever order. Okay. So next we write the complete ionic equation, and what do we have to do in that second step? Or we've got to ionize things, right? What do we not ionize? Good. You do not ionize solids and you do not ionize liquids, right? So in other words, we're going to ionize everything except for this. So ionizing, right, we're breaking it into its ions, so we need to know their charges. So first starting with the cobalt nitrate, we're going to ionize the cobalt, we're going to ionize the nitrate. So what's cobalt going to be? Good, CO2 plus. And what's nitrate going to be? Good, 2NO3, and what's the charge? -1, good. So we dealt with this guy. Now we move to sodium sulfide. So what's that going to be ionized? We're going to have 2Na plus. And what's sulfide? -2, good. So that guy's done. Next we go to the products. What should we do with this guy?
Nothing, keep it.
Nothing, right? So you're gonna just write it as it is. And then sodium nitrate, right? Because that is aqueous, we are going to ionize that. So we're gonna have 2Na plus and 2 nitrate -1. Okay. Now, what can we do from here? Good, so we could cancel the spectator ions, right? How do you identify a spectator ion? It shows up on both sides of the equation, right? So sodium is on both sides, so you can cross that off. And nitrate, you can cross off. So those are the spectator ions. Okay. Now make sure you are able to identify the spectator ions because you will be asked in a question. It'll be a precipitation reaction and it'll ask you what the spectator ions are. Okay. I guarantee she will ask you that, and because she just wants to make sure you know what that verbiage is. Okay. So after we write out after we cancel out spectator ions, we can move to our final step and write the net ionic equation, right? And that's the easiest step because you're just writing down whatever was not crossed off. So what are you left with? You're left with cobalt 2 plus sulfide gives you solid cobalt sulfide. Okay. And so the reason they're called spectator ions, right? They're just spectating, they're just watching, right? They're not contributing anything to the net reaction, right? To that net equation, right? So the analogy that I use is if I'm at a Mets game, right? If I'm a spectator at the game, am I contributing anything to the game in itself? Definitely not, right? I'm sitting down, eating a hot dog, having a beer, right? I'm not playing center field, making diving plays, right? So it's the same idea with the spectator ions, right? They're spectating, they're watching, they're not doing anything. Okay. So any questions on 18 here?
Can you write the net ionic for the reactants? Do you not need to put like aqueous?
Yeah, so you should put aqueous. I was just lazy there, but it's not going to really matter on multiple choice tests. Okay. All right. Next one, 19 here. So when a commercial drain cleaner, such as Drano, is added to a clogged drain that contains water, the following reaction happens. So this is what happens, right? So if you guys have ever used Drano to get rid of a clogged drain, like in your shower, in your sink, essentially what it does is, so this is the Al, the aluminum and the sodium hydroxide. This is what is in Drano. And what it does is it reacts with the water that's in the drain. And it does two things to clear out that clog. One, it produces a lot of heat to kind of like dissolve stuff. And it also makes hydrogen gas, which kind of just makes gas, right? It pushes stuff out. So here's the balance equation for what happens when you add Drano into a clogged drain. So I want to know if 3 grams of hydrogen gas are produced, what mass of water reacted with that Drano substance? So essentially, we're going from the grams of hydrogen to the grams of water, right? We've done that a million times. So what am I starting with here? 3 grams of H2, right? So we're going from the grams of H to the moles of H, from the moles of H to the moles of water, and then from there, from the moles of water to the grams of water, right? So to get to the moles of H, you have to use the molar mass. So what would that be? Good, 2. So I'm in the moles of H now, and I can get from the moles of H to the moles of water using my mole ratio, right? So what's the mole ratio we have here? And yes, we have 6/3, right? Now that I'm in the moles of water, I can go to the mass of water. And you would do that using the molar mass, right? So what's the answer here? How much water reacted in this problem? Good, 54 grams of water. Okay. Make sense? Oh, Peter, bro, we're here till 7:30, dude, not 7.
No, I know.
Oh, I thought you were giving me the rock. Now you're trying to get out of here, but we're almost there. We got 10 more questions. All right, are we good on 19? Does that make sense? Can I erase that? All right, take a moment to work on 20. How many moles of sodium hydroxide will react with 1.5 times 10 to the 3 grams of phosphoric acid? And I'm just one more time looking at 15. You guys, I didn't do this wrong. Sorry, just to backtrack for a moment. I think you guys might have miscounted P. But I'm just looking over my work and look. So I think what you guys might have done, and sorry to backtrack, but the P you have 2 times 2, 4. 4 here. So 2 plus 6 plus 10 plus 6 plus 1 plus 10. It's 35.
Wait, no, wait.
No.
But then how come you got 25 when you
Why do
did it
you have
again? What did
10?
you-
I
They have 10 carbon dioxides, but doesn't that mess up the
Shall I put
balance
it
of
in
oxygen on
ChatGPT?
both sides?
oxygen is
Cause that makes
20
it 20,
plus 18, 28.
38. No, that's 30. That's 38. That's 20, that's 800. But.
Wait, 20? 18. Oh my god, I'm an idiot. Yeah, no, I did it wrong then.
Well, it's trying to
Never mind. Sorry, forget about that. So it's
think of.
I'm going. So this is gonna be up on Canvas. Just know it's A. I don't know what I did on this. Yeah, I guess I can't count. All right. Does anybody have an answer for what for 20? Fif- 15. Anybody have anything else? Yeah, I've got about 46. I just didn't round, but let's see, so. I have 1.5 times 10 to the 3. So in other words, this is 1500, right? Grams of phosphoric acid. Convert grams of phosphoric acid to the moles, right? So use the molar mass. We go from the moles of phosphoric acid to the moles of sodium hydroxide, right? So what do we use to do that? The mole ratio, right? Stoichiometric coefficients. And it's a 3-to-1 ratio. So you should get 45.92 mole of NaOH. All right, we good with that? Yeah.
Why is it, what's that number under the holes? Like, on the second
Under
fraction?
this?
Or the first fraction, yeah, what's that number?
The molar mass, 98.
98. How'd you get 98?
For H3PO4, right? 3 plus P, which I think like 32. I don't know what P is off the top of my head. No, it's number 50. I don't know. Whatever. We don't have one in here, but right, hydrogen is 1 times 3 plus the mass of phosphorus plus 16 times 4. Okay. So you can just get that from the periodic table. Okay. Number 21, a chemist adds 0.4 liters of a 0.29 molar sodium chlorate solution to a reaction flask. Calculate the mass of sodium chlorate that has been added to the flask. So how do we do this? Any
Oh, the M equals moles over liters.
good? So you know you need to use the equation of molarity, right? M is moles over liters, right? So I provide you the liters, the volume. I give you the concentration. We need to figure out the mass of sodium chlorate. So we have to solve for the moles, and then from there we can go from the moles to the grams. So in order to solve this, you need to know what the formula is for sodium chlorate, right? Because you have to figure out the molar mass. So what is sodium chlorate? What's sodium chlorate? Chlorate's a polyatomic ion that, you know, yeah, good, ClO3. Right, so really please make sure we're memorizing the polyatomics, because if you don't know this, you can't answer, right? And this is an exact question from last semester. Test. All right, so what we're gonna do is we're gonna solve for the moles. Then from this, we can figure out the molar mass, and then we can find grams, right? So just to save some time, I'm gonna provide you the molar mass for this, which is 106.44 grams. That's supposed to be grams per mole. Okay. So let's plug into the molarity equation, see what we have, see what we don't have, and then we'll go from there. So we have the concentration, which is 0.29, equals the moles over liters. The moles we don't have, so that's X divided by the liters, which we do have, right, is 0.4. And so we can do some algebra here to solve for x, right? We can cross multiply, right? So 1 times x is x. Remember, x is the moles. You do the concentration 0.29 times the volume. So when you do that, x is equal to, anybody have it here? Good, 0.116 moles of the sodium chlorate. Okay, if you don't like doing the cross multiplying, you can do the triangle thing. I don't really like the triangle, but it's up to you, right? So you would set it up. M is equal to the moles over liters, right? When you're doing something over, it's dividing, right? So what did I do here to solve for moles? I multiplied the concentration by the liters, right? So you want to do it by the triangle method. You cover up what you don't have, right? So cover up the moles and you have liters times the concentration, which is that what I did there. Okay, so whatever works for you. So we get our moles of sodium chlorate. Now we can get the mass of sodium chlorate, right? So 0.116 moles multiplied by the molar mass, which is 106.44. And what's the mass that we have here? 12.3, right? So it's going to be E. Okay, any questions on that one there?
So the triangle is just kind of confusing because you would think that when you solve for you divide that by the liters.
So let's see. I'll do it in blue. So you said you think you would divide, like if you're covering up the moles, you think you would divide, right? So like,
Clarity and.
okay, yeah. So that's I've seen. So I do, yeah. A lot of people this week have gotten confused with molarity and moles. I know it sounds similar, but I mean, if the triangle confuses you, don't do that. I don't like the triangle, but if you want to use it, right, you cover up what you don't have. So we don't have moles. That doesn't exist. The M and the L are next to each other, right? So that's the same thing as saying M times L. Okay, does that make some sense?
Yeah, I mean, it's about, yeah. It's just kind of confusing with the. And versus.
Yeah, I don't like the triangle because it's easy. Like if you set it up the wrong way, you're gonna do the wrong like operation. So that's why I like to just cross multiply instead. But to each their own. All right. Number 22 says if 79 grams of zinc reacts with 163 grams of hydrofluoric acid, determine the limiting reagent. So I'll give you guys a moment to go through this.
Staying here to finish if we run.
What was that?
Are we staying here to finish if we run out of time?
We should finish.
Okay.
Yeah, I think I'm at a pretty good pace right now.
Secret. Spanish reading.
But yeah, I'll say a few like if we don't. I think if we finish on time, this will be the first semester that I finished the midterm on time.
Right.
Because usually, like, I think last semester I went like 10 or 15 over and whatever, we'll see. All right, so let's just start to go through this because the following questions are pretty long, so we are gonna pick it up a little bit. So does anybody know what the limiting reactant is here? What's the limiting reactant or limiting reagent? Same thing, right? Yeah, it should be zinc, right? So remember that the limiting reactant is the reactant that runs out first, right? So because it runs out first, it's gonna limit how much product you can make, right? So what we have to do is we have to go from the mass of each of these reactants to the mass of a product, right? Yeah. So I've seen like other books and things use that. I would say no because I don't do it that way. I've never like been taught it that way. I don't teach it that way. So we've got to, and we have to do the grant, like the gram to gram thing, because next when we do percent yield, that's like what we have to use. Okay, but good. It's a good idea. It's that's a good question. Right. So you can, whatever the limiting reactant is, it's going to limit both the products. So you can either, if it doesn't say, you can convert either to this or to this. But when I did it, I just did it to the H because it's the molar mass is easier, right? So we have 79 grams of zinc, right? I've got to convert to the moles. So now I'm the moles of zinc, and I can go from the moles of zinc to the moles of hydrogen. And then from there, from the moles of hydrogen to the moles, to the grams of hydrogen. So the 79 grams of zinc will yield 2.41 grams of hydrogen. Okay. Then we got to do the same thing for our other reactant here for the HF. So we have 163 grams of that. And same deal here. Go to the moles. From the moles of HF to the moles of H using molar ratio. So we have a 1-to-2 ratio. And then finally, the grams of H. So this amount of HF will yield you 8.15 grams of hydrogen. And so from here, right, obviously 2.41 is smaller than 8. So zinc is the limiting reactant. Zinc is going to run out first. Yeah. So you said you could do the 163 divided by 2. Yeah. So that's kind of what she asked. Honestly, I've never tried it that way. I think that works. But don't bank on that. Do it this way. Okay, but good idea. Okay, so yeah, here we have the limiting reactant, right? So zinc is gonna run out first. So how much H2 can I really make here? Can I make 8 grams? No, I can only make 2, right? So any questions about just like the concept of the limiting reactant? Does that make some sense?
Wait, can you undo it?
I don't know if I can do that.
Control Z?
Control Z. No. But see me at the end if you, and I'll post this over tomorrow. All right. A lot of talking today. 23. 50 grams of calcium carbonate is decomposed. After the reaction, 20 grams of calcium oxide is obtained. Calculate the percent yield. So what is the equation for percent yield? Good. So percent yield is actual over the theoretical times 100. Right, so the actual yield you will always be given, and the theoretical yield will be your job to figure out through stoichiometry. Okay. So we have the actual yield, right? I'm telling you how much calcium oxide we're obtaining. Now we have to figure out the theoretical yield, right? So the actual yield is, in the lab, what you actually obtain at the end of your experiment. The theoretical yield is, in theory, what you would expect to obtain through the stoichiometry, right? Very rarely do you ever actually get the theoretical yield, right? Because, there's a ton of error, you can have incomplete reactions, you can have contamination, right? It goes on and on, right? Your lab partner could be not that great, right? So we have to figure out the theoretical yield, and we're going to do that by going from the grams of calcium carbonate into the grams of CaO. So let's wait for a minute. Right, so we're going, 50 grams, not 20. Right, so we're starting with the 50 grams, we're going to the moles. The molar mass is 100. Now from the moles of calcium carbonate to the moles of calcium oxide by the mole ratio. And then finally from the moles of CaO into the grams of that by the molar mass, which is 56. So did anybody get the theoretical yield here? Anybody that solved this already? So first I want to figure out how much mass my theoretical yields. Yeah. Good. So you should get 28 grams of CaO. So that's the theoretical, and we have the actual here. So you would expect in a perfect world to make 28, but you actually only got 20 grams. So to get the percent yields, you're going to do the actual, which is 20, divided by theoretical, times 100, and you should get 71.42%. Okay, so that's a pretty good percent yield, right? It's pretty close to the theoretical value. Okay, any questions on that? Percent yield? We can memorize the equation. Yeah, cool. All right, 24. Suppose you're a chem lab TA and you have a stock 50-liter, 12 molar HCl solution. For the particular experiment with your students, you want to dilute HCl to a final concentration of 1 molar. What will the final volume be? So what are we going to have to use here?
Dilution.
Dilution, right? So we know M1 times V1 equals M2 times V2. So when you see this word stock, this is synonymous with initial, right? Stock is what you're starting with. So my initial concentration is 12 molar. My initial volume is 50 liters. And what's my final set of parameters? My final desired concentration is 1 molar. And the final volume, I've got to figure that out, right? So that will be X. Okay, so from here, hopefully some pretty simple math. 12 times 50 is 600. Equals 1 times X, which is 1X. Divide by 1, and what's our final volume? 600 liters. Okay, so I kind of use some like unrealistic numbers here, but all right. And remember X, this is V2. Hey, any questions about dilution? Okay, let's go to the next page. We're almost there. I may go a few minutes early, start a few minutes over, maybe. So 25 says, if a solution has a hydronium ion concentration of 5 times 10 to the negative 10 moles per liter, what is the pH? So what's the answer here? A, right? How do you find pH? You take the negative logarithm of the hydronium concentration, right? Remember, moles per liter is the same thing as saying molarity. So you take the negative logarithm of 5 times 10 to the negative 10, and you will get A. Okay, what if I start in pH and I want to convert that to the hydronium concentration? How would you do that?
10 to the negative.
Good. So to go to the hydronium concentration, remember these brackets mean concentration, right? You would do 10 to the negative pH. Okay, and that's because if you guys remember from high school math, logarithm has a base, an automatic base 10, right? You've got to undo that 10, and then it's got the negative, right? So it's the negative pH. Okay. So make sure you do know both of these, okay? Any questions about quantifying acids here with pH? I go to the next one. All right. 26 here. So this is she just touched on this a little bit yesterday in class. This is one of those solution stoichiometry problems, also known as titration. So just the general kind of breakdown synopsis of titration. You've probably seen videos of titration before. It's like when you have a beaker and you're adding something with a burette. It's like that glass, like skinny tube, right? And it's like that process you do when the solution turns pink. You guys ever seen that? So titration reactions are acid-base neutralization reactions, right? So the key here for neutralization is you need to know when the thing turns that light pink color, that's the what we call the equivalence point. Equivalence point. Okay. That's when the acid and base are neutralized. Equivalence point is when the moles of acid is equal to the moles of base. Okay. So this question I would say is probably on like the higher end of like questions you would be able to, have to do. Just because there's a little bit of information that you have to be able to extrapolate from here to solve, right? So in this problem, I'm asking what volume of 4 molar hydrobromic acid is required to neutralize 5 liters of 4 molar potassium hydroxide. So this is an acid-base reaction, right? So what are the products of this reaction? Right, so we're doing, sorry to cut you off, but we're doing solution stoichiometry, right? So to do stoichiometry, you need a balanced equation, right? So what are the products of acid base? Good, a salt and a water. So what's my salt? ABR, and then water, H2O. Right? So lucky us, this equation comes balanced, right? So you don't have to do any of that extra stuff. So now we're gonna, deal with the math, right? With the units and numbers I'm giving you, what formula is relevant to this? So what equation is relevant? Yeah, molarity, right? Because for the acid, so let's look at KOH, right? We have the most information for this base, right? I have molarity, so I know M is moles over liters. I have molarity. I have liters, right? From there, we're going to figure out the moles of KOH. Then for the acid to answer this problem, what we're going to do is from getting the moles of KOH, we're going to solve for the moles of HBr. And then from there, since we have both moles and concentration of HBr, we can find the volume and answer, right? So let's look at the KOH, and I'll do that in blue here. Right, we have concentration for moles we have to figure out, and the volume we do have. Right, so you cross multiply here. How many moles of KOH do you have? 20. Right? So now that I have the moles of my KOH, is there a way I can figure out? So remember what we're solving for, right? We're solving for the volume of hydrobromic acid. So that means we're going to need moles. Sorry, I'm confusing it. We're going to need concentration, which we have, right? And we're going to need moles. So from the moles of KOH, can I figure out the moles of HBr? Yes, and how would I do that? The mole ratio, right? So moles of KOH, right? It's a 1-to-1 ratio. And you just get 20 mole HBr, right? So now that I have for HBr, I have concentration, right? And I have the moles, and we can figure out the volume, the liters. So the concentration of HBr is 4 molar, equals 20 moles divided by X amount of liters. You're going to solve for X, so cross multiply. 1 times 20 is 20. Set that equal to 4 times X, which is 4X. Divide by 4, and what's the volume of hydrobromic acid? Good, I'll write it up here because I'm running out of space. X is equal to 5 liters hydrobromic acid. Okay. Yeah. Yeah, so good. That's good. That's a smart catch. Same thing. Okay, so don't always do that. It just so happens that you can be, I guess, kind of lazy and do the dilution formula. It will work, but it only works that way because it's 1-to-1 ratios. So if, let's say we had a 2 here, then that would not work. Okay, so for titration, get in the habit of doing this, because if it's not 1-to-1, then that's not gonna work. Okay,
When we see the word neutralized, we have to do that.
yeah, even though it's titration. Mhm. Have you guys done titration lab yet in your lab? No. It's tedious, but last semester I did a titration like every single day. Took a lot of time out of my life. Okay, last page here. 27. So we have aqueous sulfuric acid reacts with solid sodium hydroxide. Suppose that 10.8 grams of sulfuric acid is mixed with 15 grams sodium hydroxide. Identify the limiting reagent. So same thing here, right? You're gonna need a balanced equation. So we have a strong acid with a strong base, right? We have sulfuric acid plus sodium hydroxide gives you water and sodium sulfate. Okay. Then you would balance it. You need a 2 in front of water, a 2 in front of NaOH. And then from there you can do your stoichiometry. So here you can choose whether you want to calculate to the mass of the water or sodium sulfate. So I did it going to the mass of water just because that's an easy molar mass to get, right? So 10.8 grams sulfuric acid. Convert that to moles, right? So the molar mass is 98. Then go to the moles of water. And then to the grams of water. So with this amount of sulfuric acid, you're going to get 3.96 grams of water. And then you've got to do the same thing for the sodium hydroxide, right? So 15 grams NaOH, grams to moles. Moles to moles, right? So you're gonna use the mole ratio. So you've got a 2 mole to 2 mole ratio. And then again to the grams of water, right? So the 15 grams of base is gonna give you 6.7 5 grams of water. So what's my limiting reactant? Good, so it's A. Okay. Does that make sense? And I know it was fast, but we good okay with that? Yeah. Oh, sorry, this is a 2. That's my bad. Good catch.
That's a 90.
Yeah.
So why not sodium sulfate?
You could have done it with sodium sulfate too. You still get the same answer.
Oh.
Mhm. And then I think the molar mass is 98. Yeah. It's 98. Yeah. So the limiting reactant is going to limit both products. So yeah, so it doesn't matter. I just did it to water because I just memorized that mass, right? It's easier. Okay. All right. Almost done. Number 28. choose the reaction below that shows water acting as a Bronsted-Lowry base. So what do we think the answer is there? Good, it's C. Right? How do you know it's acting as, so first off, water is interesting because it can act as both an acid and a base, right? So we say water is amphiprotic, right? Now, we know a Bronsted-Lowry acid will donate protons, lose protons, whereas the Bronsted-Lowry base will accept protons, right? So here, water, it accepts, it gains one proton, right? So that's why it's a base in that scenario. Okay, any questions on that? So make sure you're able to identify that. This was also from the midterm last semester, so. Okay. And then finally here, number 29, and before you guys run out of here, just let me say something at the end. So sulfur dioxide is reacting with water to form sulfurous acid. What is sulfurous acid? Good, H2SO3. It's sulfurous, right? If it was sulfuric, it would have sulfate as the anion, but it's sulfurous, so it has sulfite as the anion, right? So make sure you know that distinction, right? Quick little, so if the polyatomic anion ends with ic, right? So like sulfuric, if it ends with ic, the acid gets the suffix ate. If the ion, like here, gets the suffix us, I'm sorry, it's sulfite. So if the suffix of the polyatomic ion is ite, you get the suffix in the acid us. Okay, so you can think of it, you ate something icky, or you ate something that gave you the ick, and then you took a bite of something and it was delicious. That's kind of how you can memorize that. Okay, so this equation is already balanced, right? So I want to know what mass of sulfur dioxide is needed to make 27.86 grams of the sulfurous acid. So let's do that. So my mass of the sulfurous acid so grams to moles. Now that I'm the moles of sulfurous acid, I can go to the moles of the SO2. And the equation was already balanced, right? So we didn't have to do anything there. And then from the moles of SO2 to the grams of SO2 using the molar mass, which is 64. And you should get C, 21.74 grams of SO2. All right, so that's everything you need to know for the midterm on Monday. Just quickly as a reminder before you guys get out of here, if anybody did not sign this attendance, come see me, please. In terms of Monday, I'll have my tutoring at the SLC from 3 to 5. And then I'll have my SI session from 6 to 6:50 right before your exam in General South 119, so just right next door that way. And during the SI session, I'll have some of those like echo poll problems to go over as like a last minute review. All right. So thank you guys. Have a great weekend. Good luck. I'll see you guys on
that.